Everyone, please be active in the chat box and let me know if I'm clearly audible or not. Am I audible to you? Yes, we are live. Hello, hello, hello. Yes, we are live. Chalo. What we were having discussion in the last session. Last class mein I hope we were talking about something vibration. And vibration mein natural vibration we have covered in the very first session, in the very first lecture of the vibration. Then we talked about damped vibration. And I think even the damped vibration wala part is totally over. Today, I have to talk to you about another very important phenomena, forced vibration. What is forced vibration? And this I have already told you that actually this forced vibration is very dangerous for your machineries. Right? Natural vibration doesn't practically happen. Why? Because of some weird assumptions. Unbalanced force is zero, it's okay, but friction is zero. That makes entire thing non-practical situation. Damped vibration is practical thing, but damped vibration, if it happens, depending on whether friction is less or more, if system mein friction, if system mein vibration happens, so it don't last for very long time. It will stay on in your system just for 30-40 seconds, 1 minute, max to max 2 minutes, and then this vibration is gone. So even this is not a very dangerous situation. When vibration stays for too long, that is dangerous situation for us. And this forced vibration is something which is going to be with your system until your machine runs. Till the time machine is running, vibration is going to be there. Okay. So before we jump into forced vibration directly, let me show how you can expect questions, especially if I'm talking about damped vibration. So damped vibration, there are so many formulas. I have told you so many formulas. Based on those formulas, formula based questions they can ask. Sometimes they ask questions where a little common sense logics are also required. Damped vibration mein, again, let me just give you a quick revision. What was happening, sir? Damped vibration mein amplitude was continuously decreasing, and x0, x1, x2, x3, if successive cycles ka amplitude, if this ratio I take, so that ratio is going to be constant. x0 by x1, whatever it is, x1 by x2 will be same, x1 by x2 will be same, x2 by x3 will be exactly same, and this ratio is called as decrement ratio. So first they are going to ask x0 by x1, x1 by x2, x0 by x1, x1 by x2, x2 by x3, and so on. All these things are same. Decrement ratio, e raised to the power delta we call it, and this delta is called as logarithmic decrement. Logarithmic decrement, and this delta ka value 2 pi zeta under root 1 minus zeta square, something like this we have written. So examination they will be asking, tell me what is the decrement ratio, tell me what is the logarithmic decrement. These kind of direct formula based questions they will be asking. If you know the value of zeta, delta directly, e raised to power delta directly, you can tell. Now, not very tough questions are asked. One question in GATE already they have asked for 4 marks, common data question. There was a time when common data questions were in culture. Nowadays it is not asked. 2003 they have asked this question. And what is the question? A uniform rigid cylinder bar of mass 10 kg hinged at the left end, and they have given a diagram also. Let me draw the diagram. So diagram is something like this. They have a rigid rod, horizontal position mein, one end pe, left end pe, this is hinged like this. is suspended with the help of a spring and damper arrangement as shown in the figure. Let me draw the diagram for you first. What is the diagram? Give me a second. The diagram which is given rod, we have one end pay, it is hinged. We have a spring of stiffness S Newton per meter, and we have a damper also. Damper is like this. Damping coefficient C Newton per meter per second. Dimensions where this damper and spring is connected, this is 400 mm, and this spring is connected at some 500 mm distance. And we also have a spring, this torsional, this coil Wallah spring, whose stiffness, torsional spring, its stiffness they have given as S theta something. Something they have wrong. Kilonewton meter per radian. This is torque, kilonewton meter per radian. So its unit they have given something kilonewton meter per radian, something like this they have given. So diagram is given like this. A uniform rigid cylinder bar of mass 10 kg is hinged at the left end, and it is suspended with the help of spring and damper arrangement as shown in the figure. Spring stiffness they have given 2 kilonewton per meter. So unit is 2 kilonewton per meter. Damper ka damping coefficient something C Newton per meter per second. How much is the value of C? They have given. Stiffness of the torsional spring something 1 kilonewton meter per radian. Ignore the hinge dimension. Find out what is the undamped natural frequency of this. Undamped natural frequency of oscillation for the bar about this hinge point is how much? First of all, they are asking undamped natural frequency is how much. What is the meaning of undamped natural frequency? It is omega n. They are asking. They are asking omega n ka value. What is the value of omega n? Acha, this question mein you have to be very careful about the units. So radian per second, omega n they are asking. How do I get this? How do I get this omega n? कैसे solve करेंगे भाई? Actually diagram में something like this they have given. First of all, this is a case of horizontal bar. If it was vertical, mg will also come in restoration torque, restoration couple. But here in this case, it is kept horizontal. So I am assuming that weight has already been balanced by some spring initial deflections. Okay. And can I use torque method beta? Imagine kariye, this is the mean position, and at this mean position already spring has, both these springs collectively they have deflected by some amount. So for weight has been balanced, and about this mean position, when I saw this rod was having this up down motion. When I saw, so it was moving, it has moved by some theta angle, and further theta dot velocity, theta double dot acceleration, say it was going clockwise direction. Mein torque method I am applying about this hinge point. I have discussed everything. I am just telling you how questions will be framed in front of you. So theta angle we have traveled, theta dot velocity, theta double dot acceleration, say we are moving. Now what are the torques which are acting here, sir? One torque will be given, mg ka torque I will not consider here. One torque is given by this spring. How much? It will be S stiffness, whatever distance we are connected. So this distance times theta, this value you will get. This much amount will be the force. S into, if this distance is A, so S A theta is the force multiplied by A torque. So S A square theta. Like this we write now. So it will be in this direction, anti-clockwise, S A square theta. And what is this value of S A square theta? Can I reframe this? What is the value of S stiffness? S stiffness is 2 kilonewton. Can I write this as 2000 Newton per meter? 2000 A square ka value is how much? 500 mm. So 0.5 meter mein I have converted square into theta. Can I write it like this? We have another spring. What does this spring do? Sir, this spring, because of some theta angle twist, directly it provides you torque. What this spring is going to do? Sir, this spring is to provide the forces. Linear spring hai na? So this spring will oppose any kind of deformations, elongation, contraction. It will apply some resisting forces. Force multiplied by distance, say I have achieved the torque. But this torsional spring, its work is to provide direct torque. If you will twist this, whatever toys you might have seen, childhood mein you have seen the toys. Toys mein we have some key. We twist the key and release it. So we have twisted this spring, and now it is resisting. It is just providing the torque. So unwinding it. This is how it works. Toys mein we have this kind of spring. So this will also, theta is in clockwise direction, so opposite direction it will be directly giving me torque. What will be the value of torque? Sir, it will be again clockwise theta, so anti-clockwise torque. How much? S theta, whatever is the S theta ka value, torsional stiffness, multiplied by whatever is the angle. What is the value of S theta beta? S theta is given as 1 kilonewton. That means this is 1000 Newton meter per radian. So multiplied by theta, this much Newton meter ka torque you have got. This is also something Newton meter ka torque we have got. Something Newton meter ka torque we have got. What else? We have this damper also. So damper doesn't care about at what angle you are. Damper is only resisting the velocities, relative velocities. Damper asks, I am connected at this point. Tell me this point ka what is the velocity as of now. So what is the velocity? Sir, we are moving with theta dot velocity. At 400 mm we are connected. So if I am saying that this distance is B, how do we write? Sir, in this direction, velocity ka opposite direction mein we are going to have forces. So force will be upward direction mein, and multiplied by distance, its torque will be in anti-clockwise direction. So how can we write this as C B theta dot? B theta dot is velocity, R omega. Hai na? So C into R omega, this is the velocity, multiplied by B. So C B square theta dot, this is going to be your torque. Put the values. What is the value of C? C ka value is how much beta? 500 Newton per meter per second. So the C value is 500 Newton per meter per second. C value. What is the value of B? Sir, this is 0.4 meter B square theta dot. Can I write it like this? You have written everything. Now ask DL Bhai. DL Bhai will come opposite to theta double dot. I theta dot dot I will apply, and everything will become 0. Entire summation will become 0. So this is summation of torque equal to 0. I am writing. Kya ho jayega? I theta dot dot plus, take theta common here. What you will be getting? You will be having 2000 into 0.5 square plus 1000. Let me take theta common. This is theta, and this theta dot wala term is how much beta? This theta dot ka term is 500 into 0.4 square theta dot plus something. This entire thing is equal to 0. Can I write this? This is how we can write the equation. And once we have written the equation, what is the value of I? Acha, I will be rod ka moment of inertia about one end, ml square by 3. Put the value. This is ml square by 3. What is the value of ml square by 3? M is how much? Uniform 10 kg mass and total length is given as 500 mm. So 10 kg into 500 mm, 0.5 meter square divided by 3. Put all these values and let's try to solve. Keep checking the calculation beta, hai na? Take your calculator and check what is the values I am getting. 10 into 0.5 ka square divided by 3 something 0.833 theta double dot plus this value how much? 500 into 0.4 square 80 theta dot plus what is this value? 2000 into 0.5 ka square 500 plus 1000 1500 theta is equal to 0. This is your equation. We have got our beautiful equation. Keep that in mind. This equation is not in force ka term. We have written torques. This is the inertia torque, damper, how much torque it is providing, spring, how much torque it is providing. So we have written torques. Okay. So first thing they are asking, tell me what is the value of omega n. How do we get the omega n, sir? Omega n ka value hota hai under root this divided by whatever we have here, this term. So omega n can I simply write, or let me reframe this. If you make this theta double dot coefficient as 1 divided by 0.833, so what you will get? 80 upon something 0.833 theta dot plus 1500 divided by 0.833 theta is equal to 0. So whatever we have written here, this term, can I equate this term as omega n square? This is my omega n square. I hope you remember. We generally write the equation like this, sir. X double dot plus, if this is 1, so whatever we get here, that is 2 zeta omega n x dot plus omega n square x is equal to 0. I hope you remember. Just compare, sir. Whatever it is here, that represents omega n square. So how much is the value of omega n square beta? Omega n square is 1500 divided by 0.833. 1500 divided by 0.833. Take root both sides. So I'm getting omega n something. Kitna aega? 1500 divided by 0.833. Take its root, 42.43. So omega n is coming out to be 42.43 radian per second. Check kariye if we are getting the same answer. 42.43. So option A we have got. This is correct answer. So how do I get omega n? Simple, easy. Second thing they are asking in the same question, tell me the damping coefficient in the vibration equation. What is the damping coefficient here, sir? Damping coefficient in the vibration equation, that means they are asking what is the effective damping coefficient here. Acha, if you write equation, again I am just copying this, you have got this beautiful value of equation. looks like this. Sir, equation generally it is written as mx double dot plus cx dot plus sx is equal to 0. So this is in terms of force. If I have written in terms of force equal to 0, so equation is this one, but we have written summation of torque is equal to 0. So I have got, instead of mass, I have written I theta dot dot plus something theta dot plus something theta is equal to 0. We have written like this. Now simply they are asking, tell me this damper ka damping coefficient is something. How much? This C ka value is given as 500. But in your equation, how much does it look? Sir, in my equation, what is this C value? This is 500. But how it is connected? CB is square. Its location of the damper, that also matters. So in our equation, how this damping coefficient is looking, sir, it is here 80. And both the options are there. Sir, one option they have given 500, another option is given as 80. 500 is there, 80 is there. So which you have to choose. Many people will directly say, sir, the C ka value they have given, question they have given 500. Many people write 500 is the correct answer. No. In my equation, effective damping coefficient is 80. And 80 what? In terms of torque we have written. So what is this effective damping coefficient? Its unit will be how much? Sir, this is torque, Newton meter. So Newton meter per theta dot, per angular velocity, per unit angular velocity. So Newton meter per unit radian per second. Its unit will be Newton meter per radian per second. Torque per unit angular velocity. That's going to be your effective damping coefficient ka unit. So we have 80, but which one? 80 Newton per meter per second. Do you want to call this, or you want to call Newton meter per second, Newton meter per radian per second? Sir, I will go for option C. What if we had written this equation in terms of forces? What will be unit then? Sir, at that time I will say unit of this, if this is your effective damping coefficient, then I will write this C as its unit will be, this is force, Newton per unit velocity per unit meter per second. So I hope this is clear to everyone. What is the meaning of different terms here? What will be the units? Clear hai baat? So very easy, not tough. But whenever this question was asked, many people might have done mistake here. Many people. Most of the time, gate mein simplest looking questions are most dangerous, because many people will fall in the trap of the examiner. Examiner has given a question which looks very simple. Arey sir, examiner ne pucha hai. What? Examiner has asked that tell me what is the damping coefficient. Sir, C, value of C ka value to question they have mentioned. C ka value is 500. So many people will simply say 500 Newton per meter per second. This is the value. This is the damper ka damping coefficient. But in your equation of motion, how it is behaving, they are asking this. The damping coefficient, or I can also write this as effective damping coefficient. Effective damping coefficient. You can also call it like this. Effective damping coefficient, or question they have clearly mentioned the damping coefficient in the vibration equation is given by what? Clear hai baat? So exam mein you can expect these kind of questions. Clear to everyone? Now let's talk about forced vibration. Damped vibration is over. Now let's talk about forced vibration. When I say forced vibration, bete, now I am including every parameter. I have said earlier that my vibrating system can have 3 to 4 elements. What are the 3 to 4 elements? Sir, anything which is going to vibrate, it must have some kinetic energy absorbing, kinetic energy storing element, mass, potential energy के लिए stiffness, friction and unbalanced force. These 3-4 things can be there. Now I am saying that all these 4 things are there. Now I have mass, I have some stiffness, my system is having some mass, my system is having some stiffness, some friction is also there, non-zero friction is also there, and now we are also having some unbalanced force, non-zero force is there. All these things are there. Earlier, till damped vibration, what I was saying simple, that mass, stiffness and friction is there. So I have to provide some initial disturbances. Because of those initial disturbances, my system will do something. That motion will be vibration or will not be vibration. That totally depends. That friction ka value is how much, whether this friction is dominating or not. Zeta ka value, zeta less than 1, equal to 1 or more than 1, depending on that, system vibrates or doesn't vibrate. Initial conditions, initial disturbances were provided at time t is equal to 0. How you have disturbed? I had these two, some conditions I had, but now you don't need to provide any disturbances. Why? Because your system already has some kind of unbalanced force associated with the system. Now I am talking about my all real machineries. Machineries ka matlab all those things where some moving parts are there. I am talking about my bike, I am talking about my cooler, I am talking about my ceiling fan, where moving parts are there, and those parts are not perfectly balanced. If they are not balanced, so there is some unbalanced force, and that unbalanced force is creating vibration. In your bike, we have some small piston, small size piston that reciprocates, which we haven't completely balanced. So its unbalanced force is shaking entire bike. Or in my cooler, I have 100 kg ka cooler, entire body, and inside that cooler we have 20 kg ka exhaust fan that rotates, and that 20 kg ka exhaust fan, it is not completely balanced. So when it runs at some speed, at some omega, it creates some unbalanced force, and because of that unbalanced force, entire cooler ka body is going to vibrate. Careful, very very careful. Sir, what is my system? Sir, I am talking about my cooler. Imagine kariye, this is my cooler. I have supported it to the ground. I have fixed it with the ground with some nut bolt. I have this, its mass is m. I have a cooler. This m mass is the cooler ka mass. Inside that we have some rotating part, a small exhaust fan. That exhaust fan is looking like this. This is the fan ke blades, and this mass is m dash mass. Luckily, its entire center of mass was not at the axis of rotation. It was axis say a little eccentric. How much? Maybe some distance, very small distance, e. So m dash mass, it is eccentric, e eccentric, and it is rotating with some omega angular speed. It is rotating with some omega angular speed. That omega, cooler ko, at what speed you are running, I can change also. I can change this also. I am running that cooler at first speed, second speed, third speed, 300 rpm, 500 rpm, 1000 rpm. So I can change this speed, and we can change the speed of our fan also. Even in our bike, with the help of accelerator, I can change the speed of my engine also. So this omega I can change. How much is the unbalanced force which is produced by this m dash mass? That unbalanced force will be m dash e omega square, and I'm talking about it some component. Maybe I'm talking about vertical direction mein how much is the component, or horizontal direction mein, depending on which which direction mein vibration you are looking at. Are you looking at cooler vibrates, but are you looking at this vertical vibration, or cooler ka body shakes horizontal also? Are you looking at this horizontal vibration? So whatever vibration you are talking about, this mass ka what motion you are talking about? You are talking about this motion or you're talking about this motion. In that direction, just take its component. What will be component? That component will be something cos or sine component. So I'm writing m dash e omega square sine omega t. What is this omega? This is omega at which your rotating parts are moving here. And this is also called as excitation frequency. Unbalanced force ka frequency. This omega is called as excitation frequency. Excitation frequency. Now, this entire setup I can represent mathematically. How? You can represent this setup as equivalent to rigid support के साथ somehow you have connected your entire machine. You can represent stiffness by spring. You can show whatever friction is coming from the surrounding. You can show that friction by damper, and we have this entire mass m. Looks like this. So this is my m mass. This is the damping coefficient C, Newton per meter per second. This is stiffness S, Newton per meter. And on this, some force is acting vertical direction. This is unbalanced force whose value is something. This is the constant value m dash e omega square. How much is the mass? What is the eccentricity? And what speed by you are rotating? So this is unbalanced force can be written as f naught sine omega t. I hope this is clear to everyone. So now this system mathematically I can represent like this. And now our system is going to have vibration that will remain with the system. Doesn't matter, sir, what is the value of zeta? Does it matter here? Under damped, over damped, critically damped? Doesn't matter at all. Doesn't matter how much friction you provide. Doesn't matter. System will vibrate. No one can stop the vibration. If you want that, sir, please do something. I don't want any vibration here. I will say just remove these unbalanced forces. If you cannot remove unbalanced forces, system will vibrate. It will definitely vibrate. Equation can be written as same method. Sir, this is the mean position, and about this mean position, when I saw my mass was doing vibration at any general time t, when I saw it was at x distance, and further it was moving with some v velocity, a acceleration. Can I write, sir, mass was found to be here at this location, x distance पे. So what are the forces which are going to act? Because of the spring, we will be having some Sx force. Because of this damper, I'll be having some Cx dot force, opposite to velocity. Some unbalanced force is acting here, F naught sine omega t. All the forces we have written in the direction of motion. Just ask D'Alembert bhai, opposite to acceleration, inertia force will be added here, and all this summation, entire summation will become 0. So that summation can be written as, क्या लिखेंगे? This plus this plus this minus this, because this is in opposite direction. Entire thing is become 0. So take this minus sign, opposite to the equal, it becomes positive. So I can write my equation as mx double dot plus cx dot plus sx minus f naught sine omega t equal to 0. This is your equation. That's it. This equation is called as equation of motion of forced vibration. If I take this up to the right side, it becomes positive. I can reframe this as mx double dot plus cx dot plus sx is equal to f naught sine omega t. Okay? We will further proceed with this. This is the equation of motion of forced vibration for this system. This is equation, and its solution, how that solution looks, let me directly write. I am just skipping that derivation wala part. Its solution looks like, this is equation of motion. Let me write equation of motion for forced vibration. A system which is doing forced vibration, its equation of motion is this, and its solution x is equal to complementary function plus particular integral, something like this. And complementary function after some time complementary function tends to 0, it becomes 0. So after some time, exponentially decreasing complementary function we have got, similar to the damped vibration. After some time it becomes 0. So later on, after steady state has been achieved, I will get only particular integral. So x will be particular integral only after some time, and this particular integral looks like x is equal to amplitude a sine omega t minus phi, something like this. Something like this. What is this a? This a is the amplitude of steady state vibration. What is the meaning of steady state? Steady state का मतलब होता है once your complementary function has become 0, once your decreasing nature of amplitude has stopped, complementary function once it becomes 0, then we call it as steady state. So let me write, this is after steady state has been achieved. After steady state, I get x is equal to particular integral. So after steady state examination, they ask question, tell me what is the amplitude, and if I write this amplitude, it looks like f naught by s divided by under root some big looking terms 1 minus omega by omega n whole square whole square plus 2 zeta omega by omega n square. This big two terms ka square, and don't don't get scared by this big looking formula. This big looking formula is actually very simple, very simple. Why? Because these two terms are very frequent in this chapter, multiple times. So first question they will be asking, you tell me what is the steady state amplitude. I will show you some PYQs where they have asked exactly this. Simple, they will give you all the values. What is the excitation frequency, what is the natural frequency of the system under root s by m, what is the zeta value, you can calculate, c by 2 root sm, f naught value they will give, stiffness they will give, everything they will give. Just tell me what is the steady state amplitude of the vibration. Amplitude will be everything you have put in MKS. So this amplitude will be in meter. If it is very, very small, generally it is very, very small. So you can further convert this into mm. Okay. And what is the frequency of vibration, sir? Frequency, this omega is the frequency of vibration. And how many of you can see? This is frequency of vibration. How many of you can see? Sir, frequency of the vibration is exactly same. This omega is exactly same as of your excitation frequency. Same as excitation frequency. Same as excitation frequency. Matlab, what does it mean? It means if your some rotating part is moving at 1000 RPM, so with the same frequency you will have vibration. Obvious सी बात है. So examination में, unlike other situations, natural vibration, damped vibration, they can ask, tell me what is the frequency of vibration. Here they will never ask frequency of the vibration. Why? Whatever is the force ka frequency, same frequency say your machine is going to have vibration. What they will ask? They will simply ask, tell me what is the amplitude. Simply they will ask, tell me what is the amplitude of vibration. Another term is defined here, which is called as magnification factor. Very, very careful. Magnification factor. This magnification factor is defined as the ratio of amplitude to the static deflection under the force F naught. What is the amplitude of steady state? Divided by F naught by S. I just want to compare that if this force F0 was statically acting, so how much deflection it can produce? Yani ki my mass will come how much distance under the effect of this F0 force? Sir, spring will, balance this. So up to some extent, I will see the deflections. What is that? F0 by S. But if this F0 force is acting in a fluctuating manner, I am getting the vibration of this amplitude. So yani ki this means my mass is from its mean, my mass is traveling like this. So same force, if that force F0 was gently applied, not in a shaking nature. If F0 force 100 Newton ka force gently I have applied. So initially mass was here at this mean position. 100 Newton ka force I have applied, mass spring is connected. So mass because of that 100 Newton goes only till this thing, is till this level. So this I am saying as F0 by S value. But if this same mass spring damper system is subjected to F0 force, same 100 Newton force, fluctuating nature ka force. So this mass from the mean position, it moves like this. It means from its mean, max to max, it goes here. So this value I am calling it as my amplitude. So I am just comparing amplitude and this F0 by S. I am just trying to identify what is the effect of fluctuating nature of the force. Clear hai baat? And how can I write this magnification factor? Sir, magnification factor is A upon F0 by S. It will become 1 upon some big terms. It can be written as 1 upon under root 1 minus omega by omega n square whole square plus 2 zeta omega by omega n square. Something like this. And if I'll show you the graph, but examination में this graph is very, very important. Exam में this graph is very, very important. How this graph looks, first of all, if I'll write here magnification factor, and here I am writing this omega by omega n. This omega by omega n is called as frequency ratio. So can you see that this magnification factor is depending on two things only: frequency ratio omega by omega n and zeta ka value. Can I write magnification factor is a function of zeta and frequency ratio only. Graph, how we are plotting, generally we are habitual of graph of like this, y is equal to function of c. Sir, I am plotting this y depending on x. So I will plot here x, here y. When my x is changing, how y ka value is changing. But here I am having not only two functions, I am having three functions. How this magnification factor is varying? If I increase my frequency ratio, if I change my zeta. What is the meaning of zeta? Sir, zeta is defined for a system. It is the property of system. So when I say that I am changing zeta ka value, what does it exactly mean? Zeta changing means you are changing the system. You are changing the system. For any system, zeta is constant. Zeta is property of the system. So I will plot the graph like for one system, for any system whose value is zeta something, when omega by omega and frequency ratio changes, and keep that in mind. Sir, for any system, zeta is constant, property of the system. Omega n is also property of the system. This under root stiffness by mass m. This is also property of system. So what is the meaning of omega by omega n is changing? Arey bhaiya, natural frequency omega n is constant. Omega is changing. Omega, how can we change? Arey sir, cooler ki speed I can increase or decrease. Initially cooler is not running, omega is 0. Slowly cooler ka speed I am increasing. So omega I am increasing. Getting my point? This graph, how does it look? This graph looks like a increasing decreasing curve, है ना? And let me mark two important points. One is resonance wala phenomena. What is the meaning of this resonance phenomena? Sir, resonance phenomena का मतलब होता है when this excitation frequency of the force becomes same as the omega n, natural frequency of the system. We call this phenomena as resonance. No need to fear, resonance. So this value is 1, resonance. And let me show here, this is magnification factor 1. How this graph looks. Suppose for zeta ka value 0, if we will plot the graph, put the value of zeta 0, so this term is 0. I'll get 1 upon something. 1 upon under root, this term ka square, under root goes, and I'll be having only 1 minus omega by omega n square. And as we approach towards the resonance, omega by omega n becomes 1, 1 minus 1 is 0, 1 upon 0 is infinity. So my graph looks like this. Starting from here, 1 se start hoga, every graph will start from 1 and it goes to the infinity, and after infinity it comes like this. This is the zeta is equal to 0 wala graph. If you change the zeta ka value, again graph will start from here only. It will have its peak somewhere a little earlier, earlier than resonance, and then it goes like this. Zeta ka value, this is something. I have increased something 0.5. Furthermore, if you will increase, you will get some graph, you will get the peak little earlier and smaller. So this is zeta ka value 0.8. And if I am talking about critically or overdamped system, so you will have your peak here only, and then graph further decrease, zeta more than or equal to 1. So how many of you have seen this graph earlier also, earlier in your life also? So first thing is stop fearing from this resonance. Oh sir, resonance is happening. Resonance is dangerous when we are talking about any system whose zeta ka value is 0. If your system doesn't have friction, then resonance is deadly for you. Otherwise, if your system is having some zeta ka value 0.5, so for this value, peak, whatever frequency pe peak we are having, that frequency is dangerous for you. Just avoid this peak. Either run somewhere here or run beyond this peak. And sir, magnification factor, when I say magnification factor is increasing or decreasing, it directly reflects that amplitude of vibration is increasing or decreasing. Getting my point or not? देखो भाई, force, if we are having force vibration, so if system is having unbalanced force, so vibration will be there. With what frequency? Same as the excitation frequency. So you cannot change the frequency with which vibration is going to happen. You cannot stop vibration. If unbalanced force is there, vibration will happen. So there is only one thing in your hand to save your system from the ill effect of the vibration. There is only one thing you can do, is you can try to reduce the amplitude of vibration, है ना? Let me show you the diagram, how this force vibration ka diagram is going to look. This force vibration diagram looks like this. We are having x as a function of time t, if I'll show. So initially for some time, when complementary function is alive, I'll have some decreasing function, decreasing curve like this, and after some time, when this complementary function becomes 0, I have particular integral of constant amplitude. I'll be having vibration of constant amplitude like this. So this is how we are going to have vibration. How does it look? Starting from here, vibration looks like this. Starting में amplitudes decreases, and after some time it becomes of constant amplitude, and we will keep on having this vibration. Till the time machine is running, this vibration will be there in your system. This vibration will always be there till the time machine is running. Exam mein they are going to ask only this amplitude. What is this amplitude? This is the point where I am saying after which complementary function has become 0. Steady state has been achieved. So you can only have one thing to reduce the ill effect of vibration. You can try to reduce this amplitude of vibration. Vibration will be there. With what frequency? You cannot change that. Clear hai baat? ठीक है. So magnification factor वाले ग्राफ से one thing is quite clear that we don't need to worry about resonance. If my system is something where zeta is 0, friction is 0, then you need to worry. Otherwise, if most of the time your system is having some amount of zeta, some value of zeta, some non-zero value, so you have to avoid this peak. Clear hai ye baat? Acha, let me show you how they will frame question. Acha, before I talk about question, sometimes they ask about phase angle. What is the value of phase angle? This phi which I have written here, this phi is the phase angle. Okay. How do I write the formula for the phase angle? Sir, phase angle ka simple sa formula we have tan phi. This is phase angle phi. We can write as tan phi is equal to, these are the two terms whose square we have done. Ratio of these two terms, 2 zeta omega by omega n divided by 1 minus omega by omega n square. Ratio of these two terms is called as phase angle. So still, is there anybody who is thinking that this looks very scary? No, it doesn't look scary. By denominator mein we are having two terms, under root square of these two terms. Okay, these two terms, ratio of these two terms is called as tan phi. Same these two terms we are having in the magnification factor ka formula, and same terms I'll be having in vibration isolation wala formula. है ना? What is the meaning of vibration isolation? First of all, careful. So how do we save our machine from the ill effect of the vibration? I have given you an idea. Sir, only amplitude you can reduce. How we can reduce the amplitude? Magnification factor ki graph se you are getting the idea. Then we also need to save our surrounding. Generally, this is the machine. Sir, this is the M mass ka machine, inside which we are having something, some rotating or reciprocating part we are having. M dash mass, E eccentricity, omega speed state is rotating, so M dash E omega square sine cos omega t, something like this. This is the unbalanced force your system is having because of this M dash mass. And this M mass ka machine, we have separated it by ground. We have separated this machine from the ground with the help of certain kind of supports. Supports, whatever we have used, its effective stiffness is S, and some friction which is coming from the surrounding, I'm representing as damper C. Machines go from the ground, literally, sometimes you will literally find that they are separated by some springs. Literally springs they have connected. So this is a machine mounted on some support, and that support ka stiffness and damping coefficient is this one. Sometimes you will find that literal spring is used. I just want to know that whatever force is getting developed here, F naught, this unbalanced force, whose amplitude was F naught, and because of this unbalanced force, my machine was vibrating. How to control its amplitude we just have seen. This is vibrating. But sir, its vibration is getting transferred to the ground also. And we have also witnessed this. How many of you have imagined, sir, whenever a big machine, imagine kariye, sir, even a generator, local machine, generator you can find near about your houses. Whenever a generator is running, just go and stand nearby the generator. What you will feel? Generator is vibrating, I can see this. But where generator is, standing, that if I'm very close to that generator, standing on the ground, I can feel that ground is also vibrating. That vibration is getting transferred to my body also. I'm not saying that earthquake has come because of the generator, that entire entire city is vibrating. No. But near to the generator, 10 feet, 5 feet, that area is vibrating. That area is having those vibrations. So some force was there and something has been transferred to the ground. And imagine kariye, if we have kept any other machine here, so whatever vibrations are transferred to the ground, they will be subjected to this machine also. And this machine, although it is not running, although sometimes it is not a machinery part, it is a structural part, it doesn't have any rotating or reciprocating member, but still it is also subjected to vibrations continuously and its life is also getting reduced. So not only I have to make sure safety of my machine, I also have to make sure safety of others surrounding also. That I have clearly mentioned what this is my aim. So system ko how do we make safe? We just have seen from the magnification factors graph. How do I make safe my surrounding? From this concept of vibration isolation. So let's talk about vibration isolation. Vibration isolation. So you have separated your machine which is vibrating from the ground with some kind of isolation platform. And how beautiful this isolation platform is working, for that we have defined a parameter, transmissibility. It is defined as transmitted force to the force which was developing here at the machine F0. How much force is started from here and how much it has reached to the ground, this ratio. And what do you want? Sir, I want, if my platform is working good, I want that this ratio should be less than 1. I'm not saying that this ratio is always less than 1. No. I'm saying we want this to be less than 1. We want less than 1. Then only I will say isolation is effective. Getting my point? For effective isolation, I want this term transmissibility to be less than 1. And again, I am skipping that part, derivation wala part. If you will see the result, so transmissibility comes out to be in the big formula format, and that formula looks like under root mein those big term 1 minus omega by omega n square whole square plus 2 zeta. Array sir, this is exactly same. Yes beta, exactly same, these two terms. And numerator mein what I am having? I am having under root. Here I have written 1 and this term as it is plus 2 zeta omega by omega n square. And here also if you will see the graph, similar looking graphs you are going to have, same increasing decreasing curves you are going to get. Similar fashions I will draw the graph, same fashions I will draw the graph. Careful, this is transmissibility, and here I will plot frequency ratio. This is my transmissibility 1 wala line, this is my resonance wala line, and this is my line which is representing frequency ratio root 2. This is 1, this is root 2, somewhere here we are going to have 2. This is transmissibility 1. That if you draw the graph now, how does it look? Graph looks like every graph will start from 1 increasing and decreasing nature, but the one more beautiful thing here is graph starts from here, increases, decreases, but every graph also passes through this point. At frequency ratio √2, transmissibility for every system has to be 1. So graph, how does it look? We will be having graphs like this, increases to infinity if you are talking about zeta 0, and it decreases like this, zeta is equal to 0 wala graph looks like this. For another zeta, I'll have graph increases to maximum value, decreases, and again passing through this same point. Zeta is equal to 0.5 wala graph looks like this. Any other value for the zeta ka value more than or equal to 1? What do you get, sir? Again increases, decreases, zeta is equal to more than or equal to 1. So this is how we are going to get the graphs. From this graph, again examination they will be asking questions. I will show you some PYQs. First, they ask, tell me what is the effect of increasing or decreasing the zeta. If I increase my zeta was 0, increasing. So if I increase the zeta, transmissibility increases. But wait. If you are in this zone, so zeta 0 is represented by this yellow color, zeta 0.5, zeta ka value more than, sir, if you are increasing the zeta, transmissibility is decreasing. That means beyond √2, beyond frequency ratio √2, nature is different, and below the √2, nature is different. Keep this thing in mind. Where your isolation is effective, sir, transmissibility, I don't want more than 1. I don't want to be in this zone. I want to be in this zone where transmissibility is less than 1. So let me write, this is my effective isolation zone. This is called as effective isolation zone. Effective isolation zone. You design things in such a beautiful way, you design your isolation platform in such a way that your machine runs in this zone, and even this graph suggests that for the safety of the surrounding, it's good that if you run beyond the resonance, and not only resonance, even beyond the √2, run at such a very high frequency that omega by omega n ka value is more than √2, then only transmissibility will be less than 1. So my very high speed pe my system is safe because amplitude decreases. At very high speed, my surrounding is also safe. And for the effective isolation, graphs are recommending me that best is zeta is equal to 0. That whatever machine you have, just mount this on ground with the help of only springs. No need to provide any damper. Sir, damper, most of the time damper is representing whatever friction is coming from the surrounding. Like in the fan and blade wala example, sir, friction was coming because of the air. So air ka friction symbolically damper say I have represented. But sometimes you will see that like in our bikes, we have a spring, we have literally provided damper, a spring piston, inside that some viscous fluid I have filled. So literally damper to increase the friction, we use that. And we collectively we call this spring and damper setup as shock absorber of the bike, shocker of the bike. Suna hai? So here, for the isolation purpose, I am saying that take a machine, and best will be that simply mount that machine, whatever is the machine you have, simply mount it on springs. Take whatever amount of springs is needed, only springs if you have mounted, that's best. This is best way to provide isolation. Are yes or no? Isolation. Clear hai ye baat? Tell me in the chats. BSc students are not eligible for GATE beta. MSc students are eligible for GATE. If somebody wants to give GATE examination, you can write, sir, you can do MSc. And MSc is taken as, for the GATE purpose, MSc is taken as equivalent to BTech. So I know some people who have done their MSc electronics and then they have given GATE with electronics paper. I know many people. And most of the time, these science graduates, BSc, MSc graduates, they take physics as an GATE paper. IITs में entry के लिए for the purpose of MTech, they take whatever subjects they have studied. Some people electronics say MSc, I have seen people they are doing physics. I have seen people are doing MSc. So physics paper they can choose for the GATE. Clear है बेटा? ठीक है. So this is the entire concept. Now let me show you some PYQs and I hope you can give me some answers. First, for 1 mark this question have been asked in 2014. In vibration isolation, which one of the following statement is not correct regarding the transmissibility? We have represented transmissibility by epsilon, they are mentioning it by T. ठीक है, no problem. Transmissibility is nearly unity. Transmissibility is nearly unity at small excitation frequency. What they are asking, which one is not correct? Wrong answer you have to choose. So first option they are saying transmissibility is nearly unity at a small excitation frequency. A small excitation frequency का मतलब है when omega is very very small, almost equal to 0. So when omega is almost equal to 0 or very very small, here for every zeta my transmissibility is almost near about 1. Yes sir, it is near about 1. So does it seems to be correct? Yes, it is correct. This is correct. Transmissibility can be always reduced by using higher damping at any excitation frequency. No, that's incorrect. Transmissibility always reduces by using higher damping, by increasing the damping, by increasing the zeta. Is it correct? No, this is incorrect statement. This is wrong statement. We know that, sir, if you are at this range of the excitation frequency, by increasing the zeta ka value, transmissibility increases. If you are here in this zone, by increasing the zeta ka value, transmissibility is reducing. So you cannot say that for all excitation frequency, higher damping reduces the transmissibility. No, this is incorrect option. Transmissibility is unity at the frequency ratio root 2. Sir, when frequency ratio is root 2, transmissibility for all zeta ka value it is 1. Yes, correct. Transmissibility is infinity at resonance for undamped system. Undamped system means zeta ka value 0. For zeta 0 wala system, transmissibility at resonance is how much? Infinity. Sir, this is correct? Yes, correct. So these three statements are correct. This is wrong. And they are asking me to select the not correct answer. So option B, Bombay, I will select. B, Bombay is the wrong answer here. Wrong I have to choose. ठीक है. Another question. Anyone? Can you give me the answer? They are asking simply for 1 mark. They are asking this question. They are asking, tell me what is the value of phase angle. Phase angle ka I have given you the formula. Can you try this? Take 1 minute time and tell me what is the correct answer here. Consider a single degree of freedom system with viscous damping excited by some harmonic force, unbalanced force. At resonance, when omega by omega is 1, the phase angle in degree is how much? Phase angle phi ka value they are asking is how much? बताइए. बताइए बेटा, बताइए. Anyone with answer? Time is over. Phase angle they are asking. Phase angle ka what is the formula? Simple sa formula, tan phi is equal to 2 pi zeta. Sorry. 2 zeta omega by omega n divided by 1 minus omega by omega n square. These two terms ka ratio I have to take. So at resonance, omega by omega n is given as 1. So 1 minus whatever is the value of zeta. Resonance में 1 minus 1 becomes 0. Something upon 0 is infinity. So tan phi is how much beta? Infinity. So phi is how much? Tan inverse infinity, which is 90 degree. So what is the correct answer here? Sir, 90 degree. Which option? Option C is given. 90 degree is the correct answer. So doesn't matter what is the zeta you are talking about. What is your system? Always at the resonance we are going to have 90 degree phase angle. Tell me another question. 2014 में for 2 marks this question have been asked. Calculation, simple calculation. Forced vibration. These questions look difficult. Oh, sir, big formulas are there. No, these questions are very, very simple, direct formula based questions. Tell me, what is the answer here? Mass spring dash pot. Mass is given as 10 kg. Spring constant is given as something. It is excited by a harmonic force of 10 cos 25 t. Okay. So mass I know. Spring का stiffness I know. Mass is 10 kg. Spring का stiffness is how much beta? 6250 Newton per meter. It is excited by some excitation force whose value is given as, unbalanced force is given as what? 10 cos omega t, 25 t, something Newton. At the steady state, the vibration amplitude of the mass was found to be 40 mm. Amplitude of vibration was found to be 40 mm. 40 into 10 raised to power minus 3 meter. Mm ko meter mein you have to convert. The damping coefficient C is how much? They are asking this. So how do we start this question? Sir, amplitude का formula do I know? Yes. What is the formula of amplitude? Amplitude का formula होता है f0 by s divided by under root 1 minus omega by omega n square whole square plus 2 zeta omega by omega n square. What are the values you know? Sir, amplitude is given. Okay, amplitude is given. ठीक है. f0 का value, this is my f0 का value. Omega का value is this. Omega n I can calculate from where? Sir, omega n का value होता है under root s by m. What will be the value? 625 6250 divided by 10. 625. Under root of 625 is 25. So this is coming out to be 25 Newton. Sorry, radian per second. Omega n का value I know, sir. Omega n I have calculated. Can I simply write this is the value of f naught and this 25 is the value of omega? So omega n I know, omega I know. What is the value of omega by omega n? Array, this is coming out to be 1. Resonance we are talking about. Okay. And at resonance, what will be the formula format? Amplitude becomes 1 minus 1 becomes 0. This term will come outside the root. I'll be having f naught by stiffness divided by this is 2 zeta omega by omega n, which is 1. I have simplified this formula at resonance. At resonance. देखो, difficult looking question is now very simple. All the values we know. 40 into 10 to the power minus 3 equal to f naught कितना है बेटा? F naught का value is 10 Newton. So this is 10 Newton divided by stiffness is how much? 6250. 6250 divided by 2 into zeta. Can you calculate the zeta value? From here you will get the sum zeta. Zeta is how much beta? So it is, take zeta this side, 10 upon 6250. I have got something divided by 2. Okay, something divided by 40. Okay, divided by 10 raised to the power minus 3. 0.02. So zeta ka value I have got 0.02. And if you have the zeta ka value with you, can I simply write here? Can I simply write here that zeta can be written as C by 2 under root SM. Zeta is known, stiffness mass is given, C, damping coefficient is asked. Can you calculate this? Put the values 0.02. C I have to calculate 2 under root. Stiffness is 6250. Mass is 10 kg. कितना आएगा बेटा? 6250 into 10 something. I have got under root of this 250 into 2 500 into 0.02. So C का value is coming out to be 10 Newton per meter per second. That's the answer. This simple. Matlab, there is nothing in this question. Nothing. Literally nothing. And this question was, I think, for 2 marks they have asked. So damper ka damping coefficient I have calculated. It's very easy. है ना? Let's talk about another last question. I'm just showing you that most of the time people think that post vibration, vibration isolation, these questions are sir very, very tough. Big for these are not big formulas. Only these two big looking terms, 1 minus omega by omega n square. Another term was 2 zeta omega by omega n. These terms are multiple times coming in front of you. Another is, देखो, most difficult questions can be framed in natural vibration. This is very easy. क्या पूछ रहे हैं? A single degree of freedom spring mass system with viscous damping has a spring constant something. So spring constant is given as 10 kilonewton, 10,000 Newton per meter. Okay. The system is excited by a sinusoidal force of amplitude 100 Newton. So F naught ka value is 100 Newton is given. If the damping factor is 0.25, zeta ka value is given as 0.25. The amplitude of steady state oscillation is how much? At resonance. At resonance means omega by omega n ka value when it is 1. We just have seen at, although the formula is amplitude is equal to f naught by s divided by under root 1 minus omega by omega n square whole square plus 2 zeta omega by omega n square something. This looks the formula, but at resonance this becomes 0, and formula is amplitude is equal to f naught by s divided by this 2 zeta omega by omega n comes out. Omega by omega n is 1, so I'll be having 2 zeta only. Khatam baat. Put the values. They have given you everything. F naught s zeta. That's it. What is the amplitude? Can you tell me? Sir, F naught is how much? 100 divided by stiffness is how much? 10,000 divided by 2. What is the value of zeta? 0.25. What is the value I'm getting? 100 upon 10,000 divided by 2 divided by 0.25, 0.02. So amplitude is coming out to be 0.02 meter. Convert this into mm, कितना हो जाएगा? It can be written as multiplied by 1000, 20 mm, 20 mm. That's it. So for 1 mark they have asked this question. Now tell me in the chats, if still do we have anybody here who is afraid of vibration, or sir, vibration is very tough chapter. I have heard in my college that it is very tough. Even I have a backlog in my semester examination. This is not tough at all. You, although because of the limitation of the time, I have skipped, I have not entered into the derivation part. If you go through all the details of the derivation part, you will even more enjoy this. Okay, so that's how transmissibility is having this formula. That's how solution of force vibration we have got. You will even more enjoy it. Here I have discussed only the results and how we utilize those results, and based on whatever discussion we had, I have shown you almost all the varieties of the PYQs, what kind of questions they are going to ask. ठीक है ना? So that's all. It was all about entire vibration. Vibration में most of the time natural vibration से more varieties of the questions can be asked. Damped vibration, forced vibration, this may look difficult, but it is having very limited varieties of the questions. Big variety is with the natural vibration, which practically doesn't even happen. Okay, so let's stop here. This is my code for the Telegram group. You can join this group so that we can have a continuous connection. We can have a discussion on this subject regarding your preparation. Okay, na? As of now, we will stop here. Tomorrow, when we will meet, we will talk about another very interesting chapter whose name is gyroscopic couple. So we will meet for gyroscopic couple. We will see what is the concept, what type of varieties can be asked, and then we will also see what some PYQs, what kind of questions have been actually asked in GATE, so that you can at least gain some confidence. Okay, let's stop here. We will meet tomorrow sharp at 8 for another new chapter in this series. Till that time, thank you, bacho. Goodbye. Love you all.